Hello, everyone. I am Sishun Huang from National Kaohsiung University of Science and Technology, Taiwan. Today, I want to talk about a texture descriptor called the LBP, short for Local Binary Pattern. The outline of this lecture includes introduction about the origin of LBP, binary encoding about how to use binary thresholding to form the 8-bit pattern of each point, which is referred to as local binary pattern. Non-uniform pattern handling, about the way to remove the redundant patterns resulting from noisy background. Block description about how to describe the texture of a block using the obtained LBP. LBP is a particular case of texture spectrum proposed by He and Wang in 1990. Its effectiveness of LBP was proven and described by Ojala in 1996. What is LBP? LBP is a descriptor for describing the texture of a rectangular block, and it generally consists of two steps. The first step is to encode every point in the block as a pattern called the LBP. For example, there is a 4x4 rectangular block. Then, a 3x3 mask centered at every point is used for LBP encoding. For example, the local binary pattern of the first point is 58. That of the second one is 37. Finally, we obtain the local binary patterns of all block points. According to obtain LBP, the second step is to gather statistics of LBP occurrence in the form of histogram. That is, count the number of times that a LBP appears in the given block. Thus, the x-axis of the histogram is the local binary pattern. The y-axis is the number of times that pattern occurs. Next, we talk about how to encode the point using local binary pattern. First of all, we define the texture unit, which is a basic element for LBP encoding. A texture unit generally consists of a point P to be encoded and its 8 neighborhoods. These 8 neighborhoods are located on a circle with radius r and are equally sampled. Here is a case with radius r equal to 1, and the texture unit of P is the last pointer set consisting of point P and its 8 adjacent neighborhoods P0, P1 to P7. We use this setting that texture unit is with radius r equal to 1 in the following discussion. For a texture unit of a point P in the red circle, let G be intensity of P, Gi be intensity for neighborhood point Pi. In this example, G equals to number 2, G0 is 3, and G1 is number 1, and so on. For each neighborhood point Pi, we threshold its intensity value Gi by center intensity G to obtain the binary value Si belonging to 0 or 1. If Gi is greater or equal to G, Si is 1. Otherwise, Si is 0. For example, S0 is 1 because G0 equals to 3 is greater than its center intensity equal to number 2. But S1 is 0 because G1 equal to 1 is less than its center intensity equal to number 2. Here, we show all Si. Then, we interpret the bit sequence from S7, S6 to S0 as an 8-bit unsighted integer, which is called the LBP. In this example, the LBP bit sequence of point P is 1011 1101. By considering it as an 8-bit unsighted integer, its value is 189. After encoding every point in this manner, we can obtain 256 level LBPs of all points in a given block. This shows all 256 level LBPs of all points in red rectangular block. However, encoding a point in a 256 level LBP has some disadvantages. According to the discussion in this paper, 256 level LBP is ineffective in case of noisy regions and overfitting in case of low-resolution images. The idea to handle this is to remove the LBP resulting from the noisy background. This kind of LBP is called the non-uniform LBP. In general, the pointer in noisy background has significant intensity variation. Accordingly, non-uniform LBP is thus defined as a bit sequence with more than 2 bitwise transitions, including 0 to 1 or 1 to 0. For example, bit sequence 0000 0000 has 0 bitwise transition. It is a uniform LBP. Bit sequence 0000 0001 has 1 bitwise transition. It is also a uniform LBP. Bit sequence 0000 0101 has 3 bitwise transitions, so that it is non-uniform LBP. According to the above definition, there are 58 uniform LBP and 198 non-uniform LBP in all 256 bit sequences. The way to reduce the encoding redundancy is by assigning each uniform LBP with a unique index ranging from 0 to 57, but assigning all non-uniform LBP with a single index 58. Thus, we obtain a finite level LBP encoding. By non-uniform LBP handling, the example with 256 level LBP can be then translated to finite level LBP. Finally, we gather statistics of LBP occurrence in the form of histogram as LBP descriptor. For the first point, with LBP equal to 58, we add 1 count to bit 58. For the second point, with LBP equal to 37, we add 1 count to bit 37. By visiting all points, we can obtain a LBP occurrence histogram. Furthermore, this histogram is considered as a 59-dimensional feature vector for describing the texture of the block, which is called the LBP descriptor. In order to be invariant to block size, the 59-dimensional feature vector is normalized to unity by dividing a normalization term z. Here, z is the block size, which is the number of points inside the block. In our example, the block size is 16. In this lecture, we have detailed a texture descriptor called the LBP. Thanks for your listening and have a nice day.